All right, thank you. I'm excited to be here today to talk about the doubly periodic screen configuration. This is a project I've been working on for the past 2 years, and I've been having a great time working on it. I would like to acknowledge my collaborators, Chris Eldred and Peter Caldwell. Without either of these people, I would have nothing to show today. I also want to give special thanks to Noel Keane, Chris Tried, and Hassan Beydoun. These individuals served as brave early beta testers of this configuration. So this talk will consist of two distinct parts. In part one, I will introduce this new configuration, including the motivation, the summary of development, the types of cases you can run, and how to use it. Part two, I will focus on a scientific application using this new configuration, which includes an assessment of the horizontal resolution sensitivity of the screen model. Now, in case you are new to the E3SM project or have been in a coma for the past 3 years, I'd like to briefly introduce the SCREAM model. SCREAM stands for Simple Cloud Resolving E3SM Atmosphere Model and is documented in the recent overview paper by Peter Caldwell. It is a global cloud resolving model with horizontal resolution of approximately 3 kilometers and 128 vertical levels. What Peter Caldwell concludes in his overview paper of SCREAM V0 is that moving to high resolution solves many long-standing problems associated with E3SM and traditional GCMs in general. That's very exciting, but of course you pay for what you get. Global cloud resolving models such as SCREAM are far more computationally expensive than conventional GCMs, such as E3SM. And even these relatively cheap GCMs have an even more efficient configuration, which is known as a single column model, or SCM. As depicted by this image, SCM isolates a single column of the globe and serves as a good test of the model's column physics. These columns are driven or forced by what is known as intensive observational period forcing. This forcing is often taken from observational field campaigns that we can then use to run our model in SCM mode and directly compare the simulation output to observations. Now, the biggest advantage of single column models is that they can run in a matter of minutes on a single node. Therefore, this enables fast feedback on performance of your GCM's physics in your model. These SCMs are very useful for many things. Some examples is the perfect framework to efficiently debug the model. This is obviously easier to do when you have one column versus several thousands. It is also the ideal framework for parameterization, implementation, and development. I can say this as someone who has personally both developed and implemented parameterizations into GCMs and has heavily relied on the SCM to perform these tasks. The SCM is also very useful for elucidating parameterization biases and deficiencies. Shui Zhang used it for exactly this purpose when she found an unphysical cloud oscillation in the global model in an early version of CAM6, and then she used the SCM to understand the nature of this oscillation, as well as providing recommendations to ameliorate it. Because of its efficiency, the SCM is also the ideal vehicle to perform perturbed parameter experiments and for machine learning applications. Yunyang Zhang and Charles Jackson have used this for this particular purpose to find the optimal club parameters for the shallow convective regime. In my opinion, the SCM has been an essential tool for conventional GCMs that many modeling centers rely on for efficient development of their model. E3SM has a single column model, which is great. However, SCREAM, which is far more expensive than E3SM, does not have a single column model. So why is that? Because SCREAM is a convection permitting model, this means that clouds of convection are usually resolved over several columns. SCM assumes that all cloud processes are subgrid scale, as they typically always are for 100-kilometer models, such as E3SM. Therefore, a single column model is not valid for a global cloud resolving model, such as SCREAM. While it is true that a single column model could still have some value for SCREAM in certain regimes, its appropriate use would be situational and the application would be very limited. Thus, we did not feel it was worth our while to support a single column model. However, since SCREAM is a global cloud resolving model, it is by nature a very expensive model. Thus, an efficient configuration so that we can reap all the benefits of all the bullet points I mentioned in the previous slide is very necessary. And this is something I actually felt very passionately about that SCREAM should support. Thus, the configuration we agreed on for our efficient configuration, which started as a hallway conversation about 2.5 years ago between Peter Caldwell and myself, for Scream is known as the doubly periodic Scream configuration, or DP Scream for short. DP Scream represents what I call a single point, and I'll talk a bit more what I mean by this, three-dimensional cloud resolving model on a planar grid. You can see on the right, we have the depiction of the type of model that DP Scream represents, which is a domain of 3 dimensions that is situated on a planar grid. Now, the size of this domain and the resolution of this configuration is all determined by the user. I will explain how that is done shortly. Now, depending on the specific case or IOP forcing file user wants to run, the latitude and longitude of that case is used as the location for this domain. So let's say we want to run a case over a column of the tropical Pacific water pool as depicted by this column. The DP Scream infrastructure uses the NE30 grid input files to determine the column that's closest to this point and covers our planar CRM domain with that surface type and information. This is to ensure that if we are over an ocean column, the data ocean model thinks that every column in our DP Scream model is the same latitude and longitude, and the same for the land model if we are over a land column. This is also true for the radiation parameterization, as we tell the radiation code that all columns are located at the exact same latitude and longitude for consistent radiation computation. We then initialize each column in our planar domain identically with the same temperature, moisture, and UMV winds. These initial conditions are usually provided by the IOP forcing files. Thus, at the start of the simulation, you can think of the initial state as a grid of identical SCMs. But then we apply random perturbations to the initial temperature profile to introduce heterogeneity and help to spin up the turbulence and convection. The model simulation then gets underway with any large-scale forcing being applied to the domain as needed by the IOP forcing file. And as the name suggests, the boundary conditions of this configuration are doubly periodic, so whatever goes out the right-hand side comes in the left and vice versa for the north-south boundaries. Now, I often hear people refer to DP Scream as a limited area model, and this is something of a pet peeve of mine because it really mischaracterizes what this configuration is. In a true limited area model, one might want to simulate this highlighted box on the globe and only that area with its realistic topography and surface and with the boundary conditions specified. That is also a useful configuration, but this is not what Doubly-Periodic Scream is, nor is it something that Scream currently supports. Another point I want to make, in comparison to single column models, which only exercises the model's physics because there is only one column, Doubly-Periodic Scream exercises the entire model's equation set, both the physics and dynamics. So the initial development of DP Scream was a two-step parallel effort. The first involving the infrastructure, which requires significant modification to the existing SCM infrastructure to enable its use across multiple columns and MPI tasks. Another significant step involved modifications to the PIO interfaces so that we could use the latitude and longitude of the desired case for the entire DP domain. This is to ensure, as I stated in the previous slide, that if we are over an ocean point, the data ocean model thinks that every column is the same latitude and longitude, and the same for the land model if we are over a land point. The second effort was completed by Chris Eldred, who was charged with the heroic task of developing a planar version of Home and the ability to run standalone Home dynamic core on doubly periodic planar grids. This planar configuration of Home is compatible with both the Prex and Theta L models, though Scream exclusively uses the Theta L model. And then the final step involved a multi-month effort of stitching these two development tasks together in a configuration that actually works and runs within the E3SM infrastructure. In addition to making resources so that DP Scream is accessible and very easy to use. Now, in terms of DP Scream status, the development is complete and it has been in beta testing mode for several months now. Many people who follow Scream knows that Scream has been converted to C++. However, at this time, DP Scream is only available in the F90 version. The conversion of DP Scream infrastructure to C++ will take place this year, which will be the last aspect of Scream to be converted before Scream can abandon the F90 code entirely. DP Scream is available for people to use now. However, since it is still in beta mode, there are some restrictions. However, we anticipate that the official unrestricted release is imminent. I also want to point out that Scream evaluation team has been using DP Scream to efficiently replicate biases we see in the global model. One of these biases is the so-called convection popcorn problem. This is depicted in the top panel. This bias is characterized by abundance of smaller than observed precipitation clusters and lack of organization. We were able to replicate this in DP-Scream and figure out one of the sources of error. When we fixed this source of error, it led to a 20% reduction in our popcorn convection in our doubly periodic simulation. And we also got the same exact result in our global simulation, which was a 20% reduction. Thus, we are confident that DP-Scream can provide us with a proxy to more efficiently understand this ongoing problem and help us figure out how to completely fix it much faster and much more efficiently than if this configuration was not available to us. So some of you might be wondering, so how do I go about running this? To get started, you should go to this link at the top, which represents the E3SM single column repo wiki. This repo now supports both the E3SM SCM and the doubly periodic Scream configurations. When you get to the DP-Scream homepage, you should find easy to follow instructions on how to access the scripts and information for running DP-Scream. You will note that since DP-Scream is still in beta mode, I just ask you that you shoot me an email to let me know that you are using it at this time. Now on this page, you will also find information on the case library and the types of cases you can run. Each case has a short description and a run script, which is checked out from the repo. Now, I believe that we have made running DP-Scream as easy as possible. You only need two things. The first is the most up-to-date Scream repo, and the second is a script, which you can check out from the script repo. Each case has its own script associated with it, and the minimum amount of information the user needs to supply is in the section associated with the red text. This is your basic information relating to directory paths, the machine you are using, and the account information. Now, if you were running with the default Scream resolution, which is what the script is set up to do, that's all you need to do. You simply submit the script and it will compile and submit your run. However, I want to point out that the user has complete freedom to run with whatever domain size and whatever resolution they desire, and guidance on how to change this and what the appropriate time step settings should be is provided with clear instructions in the script. So what kind of cases can you run with DP-Scream? We have a wide variety of cases that are available, ranging from continuous multi-year forcing to several deep convection cases that span a variety of convective regimes. We also have several cases that target boundary layer clouds and shallow convective cases. We are continually adding cases to our library as well, so I expect our case library will be growing very soon. And I also want to point out and take this time to thank the people who contributed substantially to this case library. So I constantly get asked what the computational expense of DP-Scream is, and it really depends on the type of case you want to run. But here I want to show you that it can provide you with rapid feedback. Here I have the cost one might anticipate for a boundary layer cloud case. These are clouds that are fairly small, as depicted by this picture, and typically require a much smaller domain size than that of a deep convective cloud case. Here we use 50 by 50 kilometers. Now at the standard Scream resolution, the cost to run one simulated day is about 4 minutes on one node on Core KNL. Now compared to the E3SM SCM, we see that the cost of DP-Scream is not that much more expensive. Thus, we are truly talking about rapid feedback provided by DP-Scream. Now, for deep convective cases, this regime typically requires a larger domain in order to adequately capture the processes and circulations and organization. For this timing, we will go with a 200 by 200 kilometer domain, which is fairly standard for most of our deep convective cases, radiative convective equilibrium excluded, of course. And at the standard Scream resolution, we can get one simulated day in 4 minutes on 6 nodes. While this is certainly more expensive than a single column model, this is still chump change. And this is still a drop in the bucket when we compare it to the cost of Scream v0, which takes 5 hours on more than 1,500 nodes to get one simulated day. Now, I want to stress that I'm not arguing that this is a replacement for the Scream global model, because there is no true substitution for that. But DP-Scream provides a valuable framework for the user if they wish to focus on a specific regime or process, or for doing debugging work without breaking the bank. A cost of 4 minutes on 6 nodes is something that virtually anyone can afford to run, and thus, in my opinion, makes DP-Scream makes running the DP Scream code base at CRM resolutions accessible to pretty much anybody. So now moving on to part 2 of the talk, I want to give an example of a scientific application of DP Scream. I've already established that DP Scream allows the user to determine the domain size and resolution on the fly. That is very different than changing the resolution in global models. Anyone who's ever made a new resolution for E3SM knows that this requires generating several input files. Now, this is a well-documented process. I've done it myself, but it can be time-consuming to fully sort out to get up and running. In DP Scream, since it is a single point CRM, changing domain size and resolution is super trivial. Therefore, we can use DP Scream to assess the horizontal resolution sensitivity of Scream as I have done. Here we seek to address 2 questions. The first is Scream scale aware, and the second is Scream scale insensitive. These are 2 terms I feel like get tossed around loosely a lot, so let me explain a little bit what I mean. By scale aware, I mean, so global Scream is supported to run at 3-kilometer resolution, but is it theoretically valid to run Scream at, say, 1 kilometers or 100-meter resolution without having to change the model code or swapping out parameterizations? We already know that since Scream does not have a deep convective parameterization, that we probably should not run it at resolutions coarser than 5 kilometers, but the validity of running at higher resolution needs to be explored. By scale insensitive, I simply mean, does the answer change when the resolution changes, and is that change substantial? Now, to do this study, we focus on 5 cases of varying regimes. However, in the interest of time today, I very briefly be going over the results from only 2 cases, a deep convective case and a marine stratocumulus case. For the deep convective case, we run at horizontal grid sizes ranging from 500 meters to 5 kilometers. And for the marine stratocumulus case, since this is run in a smaller domain and for a shorter duration, we can afford to run with horizontal grid sizes ranging from 100 meters to 5 kilometers. I want to stress that we run all cases and resolutions using the exact same code and exact same tunable parameter sets. So our marine stratocumulus case is DICOM's RFO1, which represents observed stratocumulus off the coast of California that is capped by a particularly strong inversion. This was the basis for an LES intercomparison study led by Bjorn Stevens, which featured an unusually large spread in the participating LESs. It has more or less become a go-to case to determine if a model can parameterize or simulate stratocumulus. I should note that it was found that Scream V0 does do a good job with marine stratocumulus, and it is important to note that the circulations associated with this regime are primarily subgrid scale at 3 kilometers. So this makes the DICOM's case a good first case to see how Scream performs when resolution changes and within the gray zone of boundary layer turbulence. First, we look at the horizontally averaged profiles of cloud fraction on the left, cloud liquid water on the right, to get an example of the scale sensitivity of the model or how our solution changes as the resolution changes. On the right, we have the spread of the LES intercomparison with the observations depicted by the circular points. We see that overall, for the suite of DP Scream simulations ranging from 5 kilometers to 100 meters, that the simulation of cloud liquid water is fairly robust and generally in agreement with the observations. This is especially true at the kilometer scale, by which I mean the simulations ranging from 1 to 5 kilometers. In the cloud fraction plot, however, we do see evidence of cloud thinning starting to occur at the 100-meter simulation, but again, with robust response for the configurations at the kilometer scale. Just to remind you that we are running with Scream's 128 vertical levels, which is still deemed to be too coarse to adequately simulate marine stratocumulus, which often require very high vertical resolution of about 5 to 10 meters, which could be influencing some of the results here. However, while we show that the scale sensitivity is reasonable for this regime, especially at the kilometer scale, I now want to give an example of scale awareness to show how this cloud regime is being simulated across scales is how we would expect it to be. So here we have a plot of the total vertical moisture flux produced by the Scream model for this case at all the resolutions. And while there are certainly some differences here in terms of the magnitude of fluxes, the agreement is generally reasonable for all the resolutions. What we would expect to be very different is the partitioning of these fluxes. The total moisture flux represents the sum between the subgrid scale parameterized flux and the resolved flux from dynamics. As I already stated, the circulations associated with marine stratocumulus clouds are primarily subgrid scale at the coarser CRM resolutions, such as 3 kilometers and 5 kilometers, which is what SCREAM represents, with nearly all the flux being provided by the turbulence parameterization rather than the resolved dynamics. However, at 1.5 kilometers, we definitely see we are in the so-called gray zone with this cloud regime, being partially subgrid scale and partially resolved, which is something that SCREAM is capable of handling. Once we get to 500 meters and 100-meter resolution, we see SCREAM is now primarily resolving in this regime, with the subgrid scale turbulence parameterization now playing a background role. This behavior is the hallmark of a scale-aware model and shows that without any structural changes or tuning changes to the model, it is theoretically valid to run SCREAM at finer resolutions than 3 kilometers. And this potentially opens the door to being able to use DP SCREAM as a LES process model. Though I want to point out much more validation is definitely needed on that front. For a deep convection case, we use the ARM97 case, which is a widely simulated case of continental deep convection over the ARM Southern Great Plains site. Here we focus on an 8-day subset from an active period. Now, unlike the marine stratocumulus case, this is a case where the deep convection is primarily resolved at 3 kilometers with the boundary layer turbulence and smaller shallow convective clouds handled by the subgrid scale parameterizations. Here we have the cloud profile results from our 8-day subset for cloud fraction on the left, then liquid water in the middle, and cloud ice on the right. Due to the higher computational expense of the simulation, the 100-meter simulation was not possible. However, we are currently working towards getting a 1-day case of deep convection running 400 meters. First, focusing on the more lower tropospheric cloud below 700 hectopascals associated with shallow convection, we once again see good agreement at the kilometer scale models, but a reduction of low clouds when we move to 500 meters. This is consistent with more purely shallow convective cases, which I don't have time to show today, which shows that SCREAM tends to overestimate shallow convective cloud at the kilometer scale. Focusing now on the upper tropospheric high clouds, while there are certainly some differences between the model resolutions, they all tend to show the same general behavior, which is also mirrored in the long wave cloud fluxes, which I also do not have time to show today, which is similar between the configurations. So I do want to point out that the biggest differences in the simulation seem to potentially reside in the more middle tropospheric clouds, which is associated with cumulus congestus. So once again, we'll take a look at the total vertical moisture flux of our resolution configurations to gain an understanding of the scale awareness of this regime. Unlike the Stratocumulus case, in which all of the activity was confined to the very lowest levels of the troposphere, here we see an active moisture flux extending to the upper troposphere, common for deep convection. And we also see remarkable agreement here across scales. Focusing again on the partitioning between the subgrid scale and resolved fluxes, we see that for all resolutions, the bulk of the flux is resolved by dynamics, as we would expect for a cloud resolving model simulating deep convection, with the amount of work the dicore doing gradually increasing as the resolution increases, as we see. We see that the subgrid scale parameterized flux is primarily active in the lower troposphere for the kilometer scale models, with its influence becoming much reduced when we get to the 500-meter resolution. This is because at 500 meters, the boundary layer turbulence and shallow convection is now starting to become partially resolved. So once again, while the total moisture flux is robust to changes in the resolution, how this flux is partitioned as the resolution changes represents the behavior of a scale-aware model. So to summarize, today I've introduced the Doubly-Periodic SCREAM configuration, which represents an efficient configuration of SCREAM that can be used for model development, debugging, and analysis for a particular regime or process of interest. Using DP SCREAM, I briefly showed today that we determined that SCREAM is a scale-aware model. The implications of this are that we can run SCREAM at finer resolutions than 3 kilometers without the need of making structural changes to the code or swapping out or manually shutting off parameterizations. We also determined that SCREAM appears to be reasonably scale insensitive at the kilometer scale. In other words, if SCREAM is run at resolutions from 1 to 5 kilometers, but does exhibit some sensitivity when finer resolutions are used. The implications of this are, though we don't have to make structural changes to the model code to run at these high resolutions, tuning may be required for very high resolution runs. Or alternatively, scale sensitivity could be potentially ameliorated via parameterization improvements at the coarser resolution. So is all I have today. I thank you for your time, and I will be happy to take any questions.